everybody, Jeremy Blum here with episode 5 of our Element 14 Arduino tutorial series. Today is the last day of the Arduino contest that we're running, so we'll let you know the results of that really soon. Today I'm talking about motors and transistors and a couple of new programming topics that we haven't covered yet, like for loops. We're going to use a DC motor and change its speed dynamically using a transistor and some code from the Arduino. And then we're also going to use a servo motor that you can control with PWM or pulse width modulation signals from the Arduino, control its position, and then we'll finish up this episode by making a little project that controls the precise degree rotation of a servo motor using the readings from an infrared distance sensor. Let's get started. Today we're going to be using an NPN transistor. You can see an example of one here. NPN transistors have 3 pins, a collector, a base, and an emitter. You can see in the schematic that it also has 3 pins here, collector, base, emitter. You can think of it like this. Current flows in through the collector and out through the emitter, but it's only allowed to flow through based on the state of the base pin. More current is allowed to flow through from collector to emitter as the voltage of the base pin increases. On PNP transistors, the opposite of NPN transistors, it's the opposite. When this goes low, the base, current is allowed to flow from collector to emitter. In this project, we'll be sending a PWM or pulse width modulated signal into the base, which will change the amount of current flow that goes from collector to emitter and therefore change the speed of a motor that's hooked up to this transistor. The reason you use a transistor to control a motor is because it helps isolate the motor from the Arduino and allows us to draw more current than the Arduino can provide on its own. It also allows us to operate it at 9 volts instead of 5 volts, which allows us to run the motor faster. Here's what our circuit will look like for controlling a standard DC motor. Here we can see our NPN transistor again. We have a motor connected between the collector of the NPN transistor and 9 volts. On the base, we have a 1K resistor connected from the base of the transistor to pin 9 of the Arduino, which is capable of PWM control. Pin 9 will send pulse width modulated signals through the 1K resistor to the base. We put in a 1K resistor here to isolate it from the 9 volt signal, just in case something shorts out. We don't have to worry about it breaking the Arduino. As the signal on pin 9 goes up and down, different amounts of current will be allowed to flow from 9 volts through the motor down to ground. When base is high, current will flow through the motor and allow it to turn. We also add a capacitor, 1 microfarad, and a diode pointing from the collector to 9 volts to help protect us from noise and spikes that are generally created by motors. Here's the circuit all wired up. Let's take note of a few important things. Here you can see the transistor, the capacitor, and the diode that I talked about earlier that will be controlling the motor. This is the 1K resistor that connects between the base of the transistor and pin 9 of the Arduino. The most important thing to note here, though, is that you always connect all the grounds between all of your voltages. I've used this binding post right here to connect the ground from the 9 volt battery to the ground from the 5 volt signal of the Arduino. This is to ensure that everything is operating off of the same reference level. Now we're going to write a quick program to test our new DC motor circuit. I've already gotten the framework set up. We have a motor pin connected to pin 9, and that pin is going to be configured as an output. In our loop, sometimes I like to make comments that explain to me what I want to do on the loop before I actually do it in plain English, so that I know where I'm going. This is just a generally good programming tip. So the first thing we're going to do is accelerate the motor from 0 to 255. So this will show us it changing speeds. Then we're going to hold it at its top speed for a little bit. Then decelerate it down from 255 back to 0. Hold it at 0 for a little bit, and then we'll repeat the whole thing. So the motor will accelerate, then decelerate, and then repeat. Now to accomplish this, we're going to use a new programming tactic called a for loop. So let's get that written up. And then I'll explain how it works. So here's the framework for our for loop. Basically what we're doing is we're defining a new integer called I that we're going to start at 0. And we're going to increment I by one increment every time we go through the loop up until we hit 255. So this will give us 256 different points of resolution, which is exactly how many we're able to get out of an analog output from the Arduino. And so what we'll do with each increment, we can use the I on that time through the for loop to set the speed of the motor. And we can do that using analog write motor pin I. So instead of setting a number here, we're setting it to whatever the value of I is on this time through the for loop. So the first time it goes through the for loop, I will be equal to 0, and the motor won't move. On time 100 or 101 through the for loop, I will be equal to 100, and it will set that value to 100, so the motor will be moving at about half speed. And by the time we get up to 255, the motor will be running at full speed. Now we don't want to go through this too fast, so we'll add a delay of 10 milliseconds there, so that it hangs on each value for just a little bit. Not even enough to notice for a human, but it'll make it seem like more fluid motion. Okay, and then we'll hold it at the top for a little bit. So to do that, we'll just use a standard delay function for a half second. And now we're going to do the same thing, but in reverse, to decrease it from 255 down to 0. So again, we use a for loop. We can reuse the same variable. It doesn't matter since these two for loops are completely separate from each other. So I'll just use I again. But this time we're going to start it at 255 and have it go down until it is equal to 0. And each time, instead of incrementing, it's going to decrement, which we use a double minus sign to denote, just like we use a double plus sign to denote incrementing. Always goes in brackets, and we'll do the same thing as before. Motor pin I, give it a delay of 10, and then hold it at 0 for just a little bit with a delay of a half second. Perfect. Let's see how this works. So it's programmed and the motor's doing exactly what we want it to. It spins up and then spins down and accelerates and decelerates just like it should. Great, so our transistor circuit is working perfectly. If you want to change the direction of a DC motor, you can either swap these wires or use an H-bridge to change the direction of current flow automatically. We're not going to use an H-bridge in this tutorial, but we'll probably use one in the future. It's a simple integrated circuit that you can buy that allows you to run a DC motor in both directions easily. Now we're going to control a hobbyist servo motor, like this one. Servo motors are much different from DC motors. Instead of just giving them a constant voltage and watching them rotate forever, servo motors respect a PWM signal. Depending on the value of the PWM signal, the servo will rotate to a particular location. In the case of this servo and many hobbyist servos, this one is limited to 0 to 180 degrees. Based on the value you send it, it will rotate to an exact predetermined position. This is really useful for a lot of projects. Servos take up a fair amount of current, and you could power one off of the Arduino's built-in voltage regulator. But if you want to power more than one, it's generally a good idea to put it on its own 5-volt circuit. So that's what we're going to do here, just for the purposes of demonstrating. Like we did last week, we're going to use a voltage regulator like this one. Always be sure to use your decoupling capacitors. The datasheet specifies for this voltage regulator that you should use 0.1 microfarads and 22 microfarads. The exact value isn't that important, just keep it in that general area. We'll feed in 9 volts from a battery on one end, and we'll be making a new 5-volt rail that we can power the servo off of on the other. When you're drawing schematics, you don't necessarily have to connect all the wires. Here I have 5 volts, and I'm calling this 5-volt rail number 1. You can see the little subscript 1 there. That same 5-volt rail is the one that connects to the servo. Over here, I have a separated 5-volt rail for the Arduino that it's running on. Note that the 5-volt rail should not be connected together. However, all grounds in a circuit should be connected together. Everything with this symbol, the ground symbol in the schematic, should be wired together at some point. The servo has 3 wires, a 5-volt supply wire, a ground wire, and a communication wire. This communication wire operates at a 5-volt logic level and can be connected directly to a PWM-enabled pin of the Arduino. We're going to use pin 9 again. Here we can see the circuit all wired up. You can see the servo motor here. It has 3 wires. The yellow wire goes to pin 9 on the Arduino, the red wire goes to its 5-volt supply, and the brown wire goes to ground. Note that I've disconnected the 5-volt wire from the Arduino from the board. The 2 5-volt lines should not be connected together because they're from different supplies. The grounds, however, are still connected through this lug. You can see the 2 decoupling capacitors here, and our 9-volt to 5-volt voltage regulator right here that's going to be powering the servo. We have a 9-volt battery hooked up to it. Now let's program it using the Arduino servo library so that we can get this servo doing something interesting. The Arduino programming environment has several libraries that you can use that make it easier to interact with different types of hardware. One of these libraries is the servo library, which we'll be using today to interact with our servo and make telling it what to do a little bit easier. The first thing you have to do is include any optional libraries that you want to use. So we'll include the servo.h library. You can learn more about all the libraries available to you on the arduino.cc website. After we include the files that will allow us to interact with the servos, we'll need to make a new servo object that we can control. To do that, you type servo and then whatever you want to call the servo. I'll call this one Jeremy's servo. This is creating a new object called Jeremy's servo of type servo. Now we can do stuff to that. I've already set it up as a servo on pin 9, like we always do. Note that you don't need to set it as an output manually, because when we attach the servo through the program right now, it'll take care of that for us. So we can say Jeremy's servo dot attach, and then the pin that it's connected to is the argument for that function. And you notice that this is similar syntax to the serial communication function that we were using earlier. That's because serial is also a library that Arduino uses, although it's included by default. Whereas with the servo library, you have to include it manually. Okay, so we have our servo attached to the program and ready to use. Let's make a program that will increment the servo motor about 20 degrees on an incremental basis and then rotate it back to 0. Again, we'll use our friend the for loop, which we just learned about earlier. We'll start at 0, and the servo library takes care of all the PWM commands that you need to send it. So it makes this really easy. What this for loop will do will start us out at 0 degrees, and it'll rotate us up by 20 degrees until we get to 180 degrees. And then when we're done, it'll rotate automatically back down to 0. The library automatically handles figuring out what direction it has to rotate into based on the current position and what position you want to go to. So we'll call Jeremy's servo dot right, and this will tell it the position to go to, and we'll send it to position I because we want to send it to whatever position I is in the for loop right now. Note that while before we were incrementing by 1, we can use this command to increment it by 20 each time. And we'll keep it at each spot for 1 second, just so we can see what it's doing clearly. Alright, good. Let's see how this works. Okay, so we can see that every 1 second, the servo rotates by 20 degrees, just like we asked it to. And when it's done, it automatically rotates back to 0. It's able to determine automatically what its range is and what direction to rotate in to get back to whatever position you tell it to. And it's just that simple. In fact, we can actually see that the servo is kind of walking along our breadboard a little bit here. Okay, we're going to finish up with a project that will allow us to control the position of the servo motor using the map function that we learned in the last episode and the infrared distance sensor that we used in the last episode. So let's get working on that project. Adding our infrared distance sensor to the circuit will be pretty easy. Everything else stays the same. We just add our infrared distance sensor here, connected to the common ground. You should, however, make sure that you connect it to the 5 volts from the Arduino, not the 5 volts that we're using to power the servo. This is because we want it to be off the same reference voltage that the Arduino uses for its analog to digital conversion. And then we'll connect into analog input 0 on the Arduino. Let's add the infrared distance control to our program now. This will all stay the same. We'll have to add another pin definition here. Int distance pin equals 0. Jeremy's servo will stay as it is. This can all stay the same. We don't have to define it as an input because it's an analog input and that's the default. We can get rid of our for loop because we'll no longer be using that. We can get rid of the delay. Now what we need to do is put in here a function for reading from the infrared distance sensor. So we'll make a new variable called dist, do an analog read of the distance pin, and then we'll make sure that we map that value. Remember that value comes in between 0 and 1023. So we're going to map that value to a new variable called pose, position, and 0 to 1023 will translate to 0 to 180 because that's the degrees of rotation for our servo motor. And then we'll just have that value turn the motor. So we'll set the position of the motor with the position variable. And that's it. Let's see how that works. Alright, the program's now running. Let's see how it works. Alright, great. You'll notice the servo is a little bit jerky. That's because the values coming from the infrared distance sensor are not perfect. They vary back and forth with each reading. You can fix this either by adding a filter on the input or by doing some math in the program. I'm not going to cover either of those right now, but if you want to look them up, you can. They're pretty straightforward. We'll probably be using some filters to handle analog inputs in future episodes. But for now, this is good enough, and it's pretty cool, huh? Alright, awesome. That does it for episode 5 of my Arduino tutorial series, and it's also the last basic tutorial that I'll be doing. So at this point, we've covered all of the very basic things that you need to get an Arduino up and running. The coming tutorials will be slightly more advanced and will go to the yellow LED level that I have in my difficulty rating at the beginning of each video. We'll be talking about stuff like wireless communication, serial connects between the Arduino and various integrated circuits, and things like that. It should be very educational, and I'm really looking forward to moving into some more difficult material. As always, please let me know if you have any questions or comments about these videos, or suggestions, or anything like that. I look forward to hearing from you guys, and I'll see you soon. Thanks to Element 14 for helping me to sponsor this video series. They were kind enough to provide a lot of the materials that I'll be using to create these tutorials. Feel free to go visit their website at element14.com. Check out their community, which is a great place to talk to people about electronics, the Arduino, and basically anything else engineering related. And they also have a store where you can buy a lot of the parts that we'll be using in these videos.